Okay, so we left off talking about the black body form of a star's spectrum. So in this image, you're looking at the spectrum of the sun, which is a continuous black body spectrum, the full rainbow in the background with absorption lines in front from the sun's quote-unquote atmosphere around it. So let's talk about how temperature and frequency and color all go together. So a star's temperature is dependent on the amount of energy that's coming from it. So hotter temperatures, okay, are going to be higher intensity, so they're higher frequency or shorter wavelengths. Remember, lambda is the wavelength symbol. So hot temperature stars are going to be blue and white in color. Cooler temperature stars, those yellow, orange, and red stars, they're lower intensity and they have longer wavelengths, okay, or longer wavelengths meaning that they're going to be more towards the red end of the electromagnetic spectrum. Okay, the higher energy, hotter temperature stars have shorter wavelengths, higher frequency. Okay, so what is a black body? I have mentioned it several times. So a black body is an idealized type of dense object. So this object doesn't reflect any light. Instead, it absorbs all radiation, but also emits at all wavelengths of light. It's a hot, dense object. And that radiation that it emits across the full EM spectrum, it emits this radiation entirely based on its temperature. So it's going to radiate in some frequencies or some wavelengths more prominently than others. So stars behave very much like black bodies. So the dashed line you see here is the black body curve. Notice that this actual spectral curve of our sun is very close to an idealized black body curve at that temperature. So notice that the black body curve peaks at certain wavelengths, but is still spread out over the entire electromagnetic spectrum. So here's a just more generalized view. So the black body curve, we're looking at energy output versus wavelength. So we have short wavelength on this side with the ultraviolet, long wavelength over here with the infrared. So this is the black body curve. It's the graph of an object's energy output versus its wavelength. So that peak of the energy output occurs where the temperature is the hottest, okay? So when a higher temperature object will have a higher energy output, so this peak will exist higher up. That also determines its color, right? The higher temperature objects had the more blue and white colors. So where that peak is indicates which wavelengths are more prominent, okay? So they're more prominent in the blue and the white colors and at the higher energy wavelengths. A lower peak would shift more towards the red wavelengths and be lower. So let's look at that. Okay, so this is all about thermal radiation. So as the temperature of the star increases, the peak of maximum intensity shifts to higher frequency, okay, on the left, and it goes from red to orange to white to blue hot. So as the temperature decreases, the peak of maximum intensity shifts to lower frequency or longer wavelength, and it decreases the star's relative brightness. Okay, so we'll have our hot blue or white stars, our yellow stars, and our red stars. So wave theory correctly predicts this. So notice that this middle black body here is representing a star the same temperature as our sun, so around 6,000 degrees Kelvin. Now, it's peaking in like the yellow-green, okay, but really it's the full spectrum of visible light that this peak black body is showing. So you're seeing about equal amounts of all the colors. That's going to also determine the color that you see of the star. In this case, this very bright star is peaking in the blue-purple area, so it's going to look blue in color. Whereas this low-temperature star down here is peaking in the red wavelengths, it's going to look red in color. So this plot is brightness versus wavelength, so wavelength increasing to the right. Now I've also put on here intensity versus frequency, so it's flipped of course because it's frequency. So what color is our sun? Okay, so about 6,000 degrees Kelvin. So let's look at the black body. So here's the black body curve, and here's our actual sun's curve. So as I mentioned, the sun emits wavelengths of electromagnetic radiation about equally across the visible spectrum, okay? But it emits most intensely in the yellow-green part of the spectrum. But what does it actually look like in space? It looks white, okay? Here's an image from the International Space Station. Our star actually looks white. And that's because even though the peak is in the middle of the visible spectrum at that yellow-green, it's going to appear white because the human eye really can't distinguish when it's about equally given of all the colors. Okay, so it's seeing equal amounts of the visible colors of light, and we can't really distinguish between that. So to our human eye, our sun looks white. Okay, there's two laws I want to point out when it comes to blackbody temperature curves. So first is Wiens' law, and it relates the temperature and the peak emitted wavelength. So the dominant wavelength that the blackbody emits is inversely proportional to the temperature of the object. So you don't need to worry about the formula here. Just notice that the wavelength, to get that max or that peak wavelength, which is lambda max here, is inversely proportional to the temperature in Kelvin. Okay, this is just a constant up here. So Wiens' law says that the temperature and the peak wavelength are inversely proportional. So what does this mean? So that means if we decrease the peak wavelength, okay, it means the temperature is going to increase. So as we get to smaller wavelengths, which is higher frequency, higher energy, that temperature is going to increase. As we decrease the temperature, that peak wavelength is going to shift to longer wavelengths. So the increase of intensity with temperature and decrease of the peak wavelength with the temperature. So I keep saying Kelvin, okay? So sorry my slide got cut off here, but I wanted to do a comparison of temperature scales because astronomers are going to tend to use the Kelvin temperature scale. On the left here we have frequency, in the center we have Celsius, and on the right we have Kelvin. So notice this is just another temperature scale. So 0 degrees Kelvin is also called absolute zero. This is the coldest anything can get. So even outer space is warmer than absolute zero. It's a couple degrees above absolute zero. Absolute zero is the point where the molecules that everything is made up of, the atoms and the subatomic particles, stop jiggling. Okay, even when we think something is frozen, they're still jiggling within the molecules and atoms. But at absolute zero, everything stops moving. Water freezes at 273 degrees Kelvin, and water boils at 373 degrees Kelvin. And notice that Kelvin and Celsius both increase by 100 here, okay, but 180 between freezing and boiling of Fahrenheit. So just notice your scale differences here. We're going to keep talking about Kelvin a lot in this class. Okay, the next law to talk about in terms of blackbody radiation relates the energy radiated and the temperature. So I want to introduce a new term called flux. Flux is how rapidly energy flows out of an object. And it's measured in watts per meter squared. So a black body radiates EM radiation with a total energy flux directly proportional to the fourth power of the temperature of the object. So flux is how much energy is coming out of a square meter of, let's say, a star. So if you imagine the star and you took a square meter and you measured how much energy is flowing out of that, that's the flux. So you can imagine as the temperature gets higher, the flux is going to get higher, right? But it gets higher to the amount of temperature to the fourth. So what does this mean? That means if we doubled the temperature of our star from 300 to 600 degrees Kelvin, the energy emitted from the surface each second increases by a factor of 2 to the 4. That's 16. Okay, so that flux increases by a lot if we double the temperature. Okay, so take a moment here and read this concept question, pause the video, and then check your answer. All right, hopefully you got that right. Okay, an idealized black body absorbs and emits EM radiation at all wavelengths. All right, that concludes Chapter 5. We'll move on to Chapter 6, Astronomical Tools.